What exactly is light? Today, scientists need two models to explain light and other forms of electromagnetic radiation. Waves and particles. We model radio emissions with waves because they clearly demonstrate wave characteristics, like interference. On the other hand, gamma radiation shows few wave characteristics, but single gamma photons can be detected with a Geiger counter. Sometimes both models are necessary. For example, single photons of light passing through a pair of slits will eventually produce a characteristic interference pattern. But what path does each single photon follow? The probability is high that any single photon will strike one of these bright lines. To actually calculate the shape of this probability pattern, we need to use the wavelength of the radiation. Some scientists like to think of the wave as a property of the photon particle, which is useful in determining its probable path. Strange that one model, the particle, somehow depends on another, the wave, to explain the behavior of radiation. So strange, in fact, that a university student made a daring prediction. Louis de Broglie suggested that actual particles, a piece of dust or an apple, can behave like waves. The implications of his idea seem ridiculous. Consider that day in Mudville when Mighty Casey struck out. But did Casey really strike out? Or did de Broglie? Actual particles, no matter how small, sometimes collide. If the bat and the ball are particle-like, they are capable of connecting. But waves can pass right through each other. If ball and bat are wave-like, they might be able to pass right through each other too. So was it really Casey's fault, after all? Well, de Broglie developed an equation that linked the wavelength of a particle to its mass and velocity. This de Broglie wavelength can be used to determine if an object's behavior will be particle-like or wave-like. Let's look at the implications. Consider the bat as an obstacle and the ball as an approaching wave. Wave experiments show that if the wavelength is much larger than the obstacle, the waves diffract around it easily. Our wave ball bends around the bat and carries on unchanged. But if the wavelength is much smaller than the obstacle, less diffraction occurs and a shadow region appears behind the obstacle. Our wave ball cannot bend around the bat. So, is the de Broglie wavelength of a fastball large or small? Small. so small that the ball cannot diffract around the bat if it's heading directly for it. The two collide just as we expect.
You're out!
Or at least they should collide, if Casey has his bat in the right place. To make the wavelength larger, we either need to make the mass smaller or the velocity smaller. What kind of particle might have a de Broglie wavelength that is large enough to observe wave effects like diffraction and interference? Consider one of the smallest particles, an electron. What might its de Broglie wavelength be? If its mass is 9.1 times 10 to the minus 31 kilograms. And it travels at 3 times 10 to the 6th meters per second. Although this wavelength seems small, it's no smaller than that of an X-ray. We can demonstrate the wave nature of X-rays by using, of all things, a crystal of salt. The atoms of the crystal line up to produce a series of slits running in two directions. X-rays passing through the salt crystal produce this interference pattern. Could electrons show evidence of their wave nature in the same way? The answer is yes. Electron particles passing through a crystal produce a very similar interference pattern. An electron is a particle of matter, yet it has wave characteristics, just as the photon has wave characteristics. Then is there any difference between an electron particle and an X-ray photon? There are several important differences. One of the most obvious is speed. To have a de Broglie wavelength similar to that of an X-ray photon, the electron must travel about 3.6 times 10 to the 6th meters per second. By contrast, in a vacuum, the speed of an X-ray photon is almost 100 times as great, 3 times 10 to the 8th meters per second. Another important difference is their rest mass. The electron has a rest mass of 9.1 times 10 to the minus 31 kilograms. When a photon is stopped, it is annihilated. Light is like a particle, but it's not a particle. Although de Broglie has shown us that particles and waves are themselves related, when it comes to electromagnetic radiation, the models remain just that, models. We know that light is like a particle and light is like a wave.